Okay, so let's move on to another set of examples that will use some of the techniques that we've learned before. So the example in question here is Tariq, which is me, walks into his favorite gelateria and would like a 4-scoop ice cream. And there are 3 flavors available. So he'd like 4 scoops of ice cream, and there are 3 flavors available. And the flavors are pistachio, chocolate, and salted caramel. Brilliant. We now want to sort of count how many possible combinations of ice cream there are for Tariq to choose from. If we know he wants 4 and there are only 3 available. Well, there are 2 assumptions we want to make here. One is that Tariq will try all flavors. Okay, so at least he will have at least 1 scoop of each flavor. 2, the order in which the scoops are placed on the cone or in the cup does not matter. I mean, obviously real ice cream connoisseurs understand that does matter, but let's not worry about it for today. Okay. So this problem turns out to be equivalent to asking how many solutions there are to this equation here, x1 plus x2 plus x3 equals 4, where xi is in the natural numbers. Almost, we haven't taken one of these assumptions into account, but I'll show you now. But where x1, say, is the number of scoops of pistachio, and x2 is the number of scoops of chocolate, and x3 is the number of scoops of salted caramel. Okay, so this problem boils down to asking how many solutions there are of this. Now the assumption that we make here that Tariq would like to try each flavor, i.e. that he will have at least 1 scoop of each flavor, boils down to xi are all bigger than 1. Okay? So now we're looking at this problem here, x1 plus x2 plus x3 is equal to 4, with the added assumption that xi are bigger than 1. And they are natural numbers bigger than 1. Now this thing is now equivalent to asking how many ways can I group 4 sticks into 3 groups, right? Or how can I group these 4 sticks into 3 groups where the order of the grouping matters? Now doing so corresponds to sticking 2 dividers in the gaps between these sticks. Yes? So if my big black lines are dividers, so 2 here is 3 minus 1, right? If I put 2 dividers, then I've split it into 3 groups. If I put 4 dividers, then I've split it into 5 groups, and so on and so forth. Yeah. So that means sticking 2 dividers between these sticks. So for example, here if I put the divider there and there, that corresponds to 2, all the numbers up to the first divider, plus 1, the numbers between the first and the second divider, 1, plus 1, which is the last bit there. And this has to add up to 4, because we started off with 4 sticks. And now, how many ways can we actually put dividers into these gaps is then given by how many ways can we choose a subset of gaps of size 2. Yeah. So we have 3 gaps in between these sticks, and we have 2 dividers to put it in them, and so we need to pick a subset of 2 for the dividers to go into of the gaps. We will go on to this is a sort of a warm-up example. We will go on to sort of do this sort of problem, this problem here, for a general number of x's and a general sort of equals to a general integer, and we will assume that the numbers are greater than or equal to 0 as opposed to greater than or equal to 1. Again, it depends on the problem, but we will try and generalize what we understood in this example to a more general setting. Let's consider this following lemma. Okay, so this lemma is about counting solutions to this equation where we assume xi are positive integers, right? So xi are integers bigger than or equal to 1. And we want to count how many solutions there are, how many xi, x1, x2, up to xr there are solutions to this equation. The lemma tells us that this is given by n minus 1 choose r minus 1. And the idea of the proof goes as following. If we were to sort of place the n and divide it into, or we were to place n sticks on a table like this, these are 1, 2, 3 n sticks, then a solution to this equation would mean that we would somehow divide the n sticks into r ordered groups. So here there's a bit of a gap, let's fix it in r ordered groups. Okay. So if we were to divide n sticks into r ordered groups, it's a bit like putting these dividers, r minus 1 dividers, into the n minus 1 gaps between the sticks. So we have r minus 1 dividers into n minus 1 gaps. And therefore, we need to pick a subset of size r from the set of gaps to place the dividers in. And therefore, the answer becomes n minus 1 choose r minus 1. N minus 1 here being the number of gaps, and r minus 1 here being the number of dividers we need to place into that. So here it's size r minus 1. Okay. And now we move on to the theorem. Now we're trying to count, we're doing almost the same thing, but we're going to allow here xi's to be 0. Okay. Previously we were counting positive integers, so 0 is not allowed. Now we're going to try and allow 0, we're going to allow 0 to be an xi. Okay. So we're going to have xi non-negative integers. So how do we do this? Well, we'll do a sort of intelligent substitution. We're going to define yi to be xi plus 1. Okay. Now yi is now bigger than 1. So we're basically in the setting that we have here. So each yi now is bigger than 1. And let's substitute xi equals to yi minus 1 into our equation here. Right? If we substitute it into there, then we get yi minus 1 plus yi minus 2 plus and so on and so forth, up to r minus 1 is equal to n. And now if we sort of take the ones out, then we'll have r of these ones. And if we take them to the other side, then we get an equation of this form. So a solution to this equation is equivalent to a solution to this equation, but here we're requiring, here the requirement is xi is greater than or equal to 0, but here it's yi is greater than or equal to 1, which brings us to the setting that we have in this theorem. And so we can just use this theorem to give us this answer.